Okay, so good evening, everyone. So in this problem solving session, I will present some of the sample problems of the topic so that it will help you to understand the subject better. And this will be more of an interaction session. So not that I will just present and you will listen, but we will interact. You can ask any doubt that you have, or you can also tell me the topics that you are not so comfortable with or you want to learn more that I can include in the next session. I will present some information about that particular topic. Okay. So let's get started for today. Just to confirm once, I think I'm audible and also my screen is visible. If there is an issue, please write down in the comment section. Okay, so let's see this question. Question number one. Question is the value of C for which the system of equations, the three equations, is consistent is. Okay. So what do you mean by consistent? The system of equations is consistent means that has a solution, right? A vector x, y, z which satisfies these three equations. Okay, so first thing we will do is we'll convert this system of equations into a matrix form. So always a system of equations like this can be represented in a matrix form as Ax equals to B, whereas A will be the matrix formed by the rows of these equations, then it will be the coefficients of the vector x. So when I say x, don't confuse with the already existed variables x, y, z. Maybe I'll write something else. What should I write? A u equals to b, maybe, let's say. The u is your vector x, y, z. So A will be a matrix now, 3 cross 3, because there are 3 rows and 3 variables, where each row consisting of the coefficients of the vectors x of the variables x, y, z in each row. For example, the first row, coefficients of the variables x, y, z are 1, 1, 1. Hence, the first row will be 1, 1, 1. Second row will be 3, 2, 1. Third row will be 4, 3, and C. Now B will be the right hand side column vector, which will be 1, 2, 3. So the question is whether the system AU equals to B has a solution or not. Yes, someone raised the hand. What's the issue? Yeah, Deepa Lakshmi. Is there something problem? Okay, I think it's by mistake. Okay, so the formula, first of all, is the system of equations AU equals to B is consistent if and only if, I'll write it here. Is consistent if and only if rank of the matrix A will be same as rank of the matrix A augmented B. What is A augmented B? Where A augmented B is the matrix A and you add B as the next column, right? In this case, A will be as it is 1, 1, 1, 3, 2, 1, 4, 3, C, and the last column will be B. Now this will be a 3 cross 4 vector matrix. So when the rank of A and this new newly created matrix A augmented B are same, then we say the system is consistent. So the only task we have to do is we have to find out what is the rank of A and then what is the rank of A augmented B. So and that will involve some condition on C, and that will be our answer. Let's see. I'll just convert this A augmented B into row echelon form. So I have to do third row minus 3 times first row. So 3 minus 3, 0. 2 minus 3 minus 1. 1 minus 3 minus 2. Please correct me if I'm making some mistake. Then 2 minus 3 again minus 1. So third row minus 4 times first row. So 0, 3 minus 4 minus 1, C minus 4, and then minus 1. Okay, then, so here I made the operations as R2 changes to R2 minus 3 times R1, and R3 changes to R3 minus 4 times R1 in order to make these two entries 0, because the first row you have 1 here, so the entries below that um, entry in that column will has to be 0. By the way, because of some technical issue in this session, I cannot turn on my camera. It's not opening somehow. But from the next sessions, the camera will also be on. So I'm sorry for the inconvenience. So these are the operations that I have made for this one step. Now in the next step, this is the similarity notion. This is again similar to 1, 1, 1, 1. Then I'll just multiply this by plus 1. And then I'll add in the third row, 0, minus 1 plus 1, 0, C minus 4 plus 2, C minus 2, and then minus 1 plus 1, 0. So we have observed is this until here we have the matrix A and then the matrix A augmented B. So if C equals to 2, then what will happen? Okay, imagine if C is not 2, then you will have rank of A is 3, which will also be rank of A augmented B. And if C equals to 2, then what's happening? If C equals to 2, then rank of A will be 2, and which will be again same as rank of A augmented B. So this system always has the system is always consistent. Am I correct? Or is there any mistake? Yes, yes. I think the question I had some mistake here. I mean, there is no condition on C. No matter what C you choose, the system is always consistent. Okay, I can give you a solution as U equals to 0, 1, 0. 0, 1, 0 is always a solution. No matter what value of C you choose, the system is always consistent. Okay, so don't think of these options because there is no sense on C. There is no condition on C. So this is how you see what's the how to check whether a system is consistent or not. You calculate rank of A, calculate rank of A augmented B, and see the conditions under which the ranks are same. Is there any doubt in this question? You can either raise hand or type it in the chat box so that I can repeat. Okay. If no doubt, sir, go ahead. Now the system of equations x plus y plus 3z these three equations are there, and we have to check whether this system has unique solution, infinitely many solutions, no solutions, or like two solutions, which can never be the case. Okay. So same way we'll formulate this system of equations into matrix form as AU equals to B So your matrix A will be 1, 1, 3, 2, 3, minus 1, 5, 7, 1. And your column vector B is 1, 3, 7. You have to see whether the system has a solution or oh, like no solution. Okay. So first thing, of course, we will do is whether the system is consistent or not. Okay, right? If its system is consistent, then we'll see how many solutions does it have. If not, then there is no solution. So the same method will start with A augmented B, which is the matrix 1, 1, 3, 2, 3, minus 1, and 5, 7, 1. The I'll add as the last column as the B vector 1, 3, 7. Then I'll perform some row operation. So first operation will be changes to R2 changes to R2 minus 2 R1 and R3 changes to R3 minus 5 R1. With this change, I will get a matrix as 0, then 3 minus 2, 1, then minus 1, minus 6 is minus 7, and then 3 minus 2 is plus 1, and then 0, here we get 0, then 2, 1 minus 15 minus 14, then 7 minus 5 again 2. Now I'll change R3 as R3 changes to R3 minus 2 R1, R2. With this change, I'll get the matrix as first and second rows remain as it is. And then last row will become 0 minus 0, 0, 2 minus 2, 0, then minus 14, minus minus plus 7 to the 14, again 0, and then the last, yeah, again 0. What we get is rank of A is same as rank of A augmented B. That means system is consistent. Now the formula to check whether how many solutions are there is that if let's say rank of A and rank of A augmented B is equals to K. Okay, so we know that K lies between 1 to n, where n is the number of columns of A, right? So first condition will be if K equals to n, then we have unique solution. And second is if K is strictly less than n, then there are infinitely many solutions. So what's the case here? We have rank of A and rank of A augmented B. This is the symbol for rank. Is equals to 2, which is strictly less than 3, which is number of columns, since we have infinitely many solutions. But does anyone know these two statements? I mean, why is this the case that if rank of A is less than n, then we get infinitely many solutions? Anyone? Does anyone know why? Or if you want to explain, you can also write that in the chat box that you want to know why this is the case. How do we get infinitely many solutions if K is strictly less than n? Okay, if someone know, they can just turn on their mic and speak, because then it will be more of a lively class and like more interactions.
Sir, shall I, sir?
Yeah, please, please.
Uh, Sir, in the last matrix, we will get two equations, but we have to find three unknowns. So there
Yes.
will be infinitely many solutions.
Okay. Yeah. So you have to determine three variables by using two equations. That's the reason you're saying, right? Yes. Yeah. Yeah, that's true. Partially true. I'll explain with one more another method that's more mathematical. How can you give infinitely many solutions? I mean, so there is something called rank nullity theorem. The students from mathematics background will know this theorem, and those of engineering background, I will tell what is it. First thing is what is a rank? I mean, consider A as an operator from Rn to Rn. Every matrix is itself an operator, you can think of. Operator means it's a linear map from Rn to Rn. Okay. Then the rank of A is the dimension of range space of A, and nullity of A is the dimension of null space of A. What is the null space of A? Null space of A is set of all x belongs to Rn. Okay, now we are referring U. So therefore U belongs to Rn such that AU is 0. Okay, the vectors which maps to 0 under A. That's nullity. That's null space of A, and dimension of the null space is called as nullity. So rank nullity theorem states that for any linear operator A from Rn to in fact Rm doesn't matter. For any linear operator A from Rn to Rm, its rank plus its nullity is always equal to n. Okay, this is the rank nullity theorem. It's a very important theorem in finite dimensional linear algebra. Now, with help of this example, what we can say, if rank of A is strictly less than n and system is consistent, of course, then only we'll talk about number of solutions, right? System is consistent. Now, from this equation, if rank is less than n, then what do we know? We get that nullity will be strictly greater than zero, right? Or strictly, yes, strictly greater than zero. That means there exists also some, well, what will I denote? Maybe V belongs to Rn such that AB is 0. Why? Because see, because the rank of A is strictly less than n, nullity has to be some non-zero number, so that addition will be n. Hence, the nullity dimension of the null space of A is positive. That means there exists at least some non-zero u for which AU gets 0. That's I'll call that vector as V. Now, because system is consistent, let's say let U be the solution of a systematic equation of given system Ax equals to B. Sorry. Okay, the system is AU equals to B we have, so I have to call solution as something else. Okay, that's a tough task asked. What should I name the variable? UVW, let's say. Let W be the solution of the given system AU equals to B. That is, I mean, we have AW equals to B, and we know AB equals to 0. So now I'll give some infinitely many solution as A at W plus alpha V. What will be this? Because of the linearity, that will split as AW plus alpha times AV. But I know that AV is 0. So this is alpha times 0, which is, okay, the page. This is AW plus alpha times 0 is 0. But from here, what is AW? It's again B. So for any alpha belongs to real number, I get alpha, this new element. W plus alpha V is again a solution, right? So in this way, I get infinitely many solutions if the rank of A is strictly less than n. I hope this is clear. Now answer to this question is 2 because we have rank of A and the same as rank of A augmented B, which is less than 3. Okay, let's go to question number 3. Applying an elementary row operation, R2 changes to R2 plus 3R1, a matrix A is reduced to B, where if A equals to P inverse B, then the matrix P is. Okay, A equals to P inverse B, it's same as saying that PA is equals to B. We multiply P from left side to the equation and from both sides. Then we get PA equals to B. Now, whenever you do this row operations, some R2 changes to same like this, linear combination of rows. That means you are multiplying A with some elementary matrix, right? So how you find that elementary matrix is you apply the same elementary operations on I, the same operations, and then you get P. This is your matrix P. So identity is my matrix 0, this, and then I'll change R2 changes to R2 plus 3 R1. Then I'll get the matrix as 3 1 0 0 0 1. And which one is that? So this is the option number D. So this is a very simple problem. Okay, let A be the matrix of order n cross n. Which of the following is true? A minus A transpose is symmetric. Okay, let's see. So by symmetric, a matrix symmetric if its transpose is the same as the matrix, right? So what will be A minus A transpose? Transpose. Transpose is a linear operation, so I can take the transpose in between. That will be same as A transpose minus A, but this is minus of A minus A transpose. So I started with a matrix. I will call this as X, and I get a new matrix as minus X. X transpose as minus X. So this A minus A transpose is not symmetric. This is the wrong option. Then I have A transpose is symmetric matrix, but A minus A transpose. Oh, that's a problem. Just give me a minute. Okay, I'm sorry for that. Yeah, so first option is wrong. Let's see what second option says. A transpose is symmetric. Okay, so what is the transpose of A transpose? It will switch like The formula we know is for any matrix is A and B, AB transpose is B transpose A transpose. So with that, what will be A transpose is transpose? It will be A transpose transpose and then A transpose. This is B, this is A in our case. This is A transpose again. So the matrix that we have started with is same, the transpose of the matrix is same as the same matrix. So A transpose is symmetric. And as we have seen here earlier, A minus A transpose is skew symmetric. Yes, X transpose is minus of X. That is the definition of skew symmetric matrices. So option 2 is correct. So you can check the rest too. That will be wrong. Let's go to the next question. Okay. A be a matrix of order 3 cross 3 so that determinant of A is minus 3. Let B be the matrix obtained by swapping the first two rows of A, then the value of determinant of 2 times B whole transpose is. Okay, there are certain row formula that I will use. First one is for any matrix A, determinant of A transpose will be same as determinant of A. Second one is determinant of lambda A will be uh, lambda lambda raised to n determinant of A, where n is the order of A, matrix A. Okay, maybe these two formulas are enough. Yeah, and if you swap the two rows of a matrix A, then the determinant will be multiplied by minus 1. So that's another formula. So with this, what will be determinant of 2b? Determinant of 2b transpose the same as determinant of 2b, which is same as 2 raised to 3 times determinant of b. And b is a matrix obtained by swapping first two rows of A, so determinant of b will be minus of determinant of A, which is 8 times 3, 24. Option number C. Okay, so just as a uh, more information, why is this formula there? Determinant of lambda A is lambda power n times determinant of A. So what happens if I multiply a matrix only one row by some non-zero alpha? Like consider this matrix maybe. Okay, let's just take the identity matrix. Okay, this is the identity matrix. Now what if I multiply the last row by 5? What will be the determinant of this matrix? Can someone tell me? Hello. Okay, so I mean this is very okay, this the determinant of this matrix is 5. The point that I wanted to imply from this example is that if you multiply certain row of a matrix, then that entry will be multiplied to its matrix, to its determinant. So it is 5 times determinant of identity matrix, which is 1. Hence the determinant is 5, right? Another way of saying this is determinant function is linear in each row. Okay. So if you consider the rows of the matrix as, I'll call this as R1, then this is as R2, then this is R3. So, and determinant I'll call as a function from R n cross n to R. Okay, someone raised a hand, or was it by mistake? I think it's a mistake. Okay, Vishnu Priyad, you have raised a hand. You have any problem? Yes. Please be careful with the raising hand. Button is very annoying. The determinant is considered as a function from Rn cross Rn. This is the set of all matrices easily denoted as Rn cross Rn, two real numbers. The determinant function, so any matrix when considered as a kind of set of rows, right? The first row R1, second row R2, third row R3. Then if you keep all the rows same and multiply only some particular row, for example, say R1, R2, and then some kth row I'll multiply by alpha, and then this is Rk plus 1, and then Rn. Like if you just multiply one row and keep all the rows same, then this is linear in that row. So it will be alpha times determinant of R1, R2, Rk plus 1 till Rn. So this is the thing. This happens for every k. So the main motto to say this is that determinant function is linear in each row, keeping all the other rows same. So when you multiply a matrix by one scalar lambda, then you multiply each row by that scalar lambda, right? So determinant of what is determinant of this? So you do the same operation as here, but each time for just one fixed row. For example, here you keep all these entries same and use the above formula for just first row. Then it will be lambda times determinant of R1 comma lambda R2 until lambda Rn. Then you do the same operation again. Then another lambda will come from the second row, and you will be with R1, R2, lambda R3 until lambda Rn. And you do it repeatedly n times, and you will end up with n copies of lambda here in multiplication, and then determinant of R1, R2 till Rn. Okay, so that's all. This is your matrix A. So determinant of A, and this was determinant of lambda A. It's a lambda determinant of lambda A is lambda raised to n times determinant of A. This was the logic behind this formula. And for transposes, it's the same. I mean, not a big deal. You can represent the matrix as a function of rows also and a function of columns also. That will be the same. Okay, now let's go to question number 6. Anyone has any doubt in the previous questions? Okay, if not, go ahead. Which of the following set is linearly independent? So linear independency, what is mean by a set to be linearly independent? So you can name, I mean, consider any set for in general, and I'll define abstract definition of independency. Consider S to be a set of vectors, maybe u1, u2 up to un, subset of any vector space V. Because this is just a matrix analysis course, so we will deal with Rn. So a subset of Rn is said to be linearly independent. The abstract definition is that if it if following holds, that is summation, I'll just write alpha 1 u1 until alpha n un equals to 0 should imply that all alpha i's are 0. Okay, that means if you equate this linear equation as 0, then the scalars has to be 0. The only way the linear combination is 0 is the 0 way. This is the definition of linear independency, and if you want to imply this abstract definition in Rn, the easier way will be, because these UIs are now column vectors, you can consider, for example, these 1 2 1 2 1 3 3 3 4. You put these UIs as columns of the matrix u1, u2 until un. This is the first column, this is second column, this is the nth column, and then S is linearly independent if and only if, I'll call this matrix as A, rank of A is n. That's all. In Rn, the linear independency will boil down to the rank of matrix being equal to number of uh, vectors. Now the question is very simple. You have to just put those vectors in columns of A and just figure out what's the rank. Okay, I can leave these to you. You can verify this one. It's easy. I will share the whole PDF of this presentation with you so that you can refer the questions and the solutions. Now, the number of non-zero rows in the equivalent form of this matrix is. This is a very methodological question. You just have to start, convert each row. I mean, you can convert this into standard row equivalent form and then see what the number of non-zero rows. In fact, the number of non-zero rows will be the rank of the matrix. So yeah, this is a very easy question again. I will leave this for you as an exercise. I hope that's clear. If anyone have any doubts in this, last question answer. Question number 6 answer. You are saying no, I don't know the answer. You can try by yourself and see. And that's not a difficult question, right? Just to verify. And by the way, I don't think this is the assignment that you have in the course. These are the different questions. I hope. Does anyone can anyone just reply and tell me whether these are the same questions? Oh, someone is presenting. Uh, uh, so yeah, please, thank you. Hello, hello. Is my voice clear? Yeah, I will try to speak more loud. Just let me know when it's annoying. Also, if it's very low, please let me know. Thank you for the response, Madhavi R. Let me know if this is now audible properly.
Yes, sir.
Okay, thank you. Okay. The number of non-zero rows, this is a easy task. I will leave this as an exercise. Let's go to the next question. Okay, they have given a matrix A. A linear system Ax equal to B is inconsistent for any B belongs to R. Then the rank of matrix A augmented B is. Okay. So we have seen before that the linear system is consistent if and only if rank of A is same as rank of A augmented B, right? So that if the A system is inconsistent, that means rank of A augmented B has to be more than rank of A. Right? So we'll just can calculate what is the rank of A. So I'll do some operations here. So R2 goes to R2 plus 3 R1 because we already have minus 3 here. So I'll just add up the 3. Minus 3 plus 3, 0. Then 3 minus 6. Minus 3 and 0 minus 6 and minus 3. Then R3 will change to R3 minus 2 R1. That will give me 3 minus 2, so 2 minus 2, 0, 2 and minus plus 2, 4. Then 4 plus 2, 6. Problem in this question. Okay, so what will be rank of this matrix? Divided by minus 3, so okay. So minus 4, 0. The rank of A is 3 here. So because every vector is in the range, that means there cannot exist such a B, so that the system is inconsistent. So there is something wrong in this question. I hope I made some right calculations. If anyone seen any mistake, please let me know while calculating the rank of the matrix A. Okay, maybe it's okay. Maybe there is some some problem in the question. There cannot exist such a B, so that the system is inconsistent. Let's move to the next question. The value of k for which the column vectors of the matrix are linearly dependent is okay. So when do you say that the columns are linearly dependent? As I've explained before, that the columns are linearly independent if and only if the rank of the matrix is n. So just we have to find out for what values of k the rank is less than n. Let's do some row operations. For simplicity, I'll swap first and second row. 1k0, then 2, 1, 3, then minus 4, 3, minus 1. This will change to okay, there is some problem. Can everyone see my screen?
Yes, sir.
So it's frozen, right? Just 1 minute.
Yes, sir.
Just give me a minute. Meanwhile, you can calculate the rank of this matrix. So anyone can just let me know the answer. This auto update, my Gmail app is being auto updated. Yeah, I mean, who raised a hand? You can tell me what's the problem. Ajisha.
Yes, sir.
Yeah, what's the problem? You raised your hand. Yeah, okay. The app is back. Yeah, I hope it's visible now. Anyone just confirm? Yeah, no, I think it's visible. Okay. So I'll perform some row operations now. 1k0 is the first row. Second row changes to r2 minus 2r1, and third row changes to r3 plus 4r1. So that will be 2, 0, 1 minus 2k, and then 3. Then this is 0, this is 3 plus 4k, and then this is minus 1. Okay. Now I'll again have to change. Hmm. Okay. This is interesting now. I have to do some row operations in order to make this entry 0. Can anyone tell me what I should multiply? What I want is I have to make some changes. 3 plus 4k multiplied by some alpha times 1 minus 2k should be 0. What is that alpha? Simply I'll get 3 plus alpha plus r coefficients of k, 4 minus 2 alpha times k plus 3 plus alpha has to be 0. Yes, there is no point. No, so let's take alpha to be minus 3 plus 4k divided by 1 minus 2k, or simply 3 plus 4k divided by 2k minus 1. But this is complicated. Okay, let's think of something else. Maybe this happened because I switched the first and second rows. Okay, let's not switch and then see what happens. So it's 2, 1, 3, and 1. Now the same method. Now 2 times this minus first row. This is 0, then 2k minus 1, then minus 3, then R3 plus 2 times first row. This is 0, 3 plus 2 is 5, minus 1 plus 2. This is again 5. And now 3. Now I have to make this entry 0. Okay, so or I'll change the second and third row 0, 1, 1. I have divided this by 5 and then that's it. Hmm. Okay, so if yeah, okay, for converting this matrix into row echelon form, I have to multiply this second row by some alpha and subtract or add into this equation, right? And then for rank of A has to be, I mean, less than 3 if and only if 2k minus 1 will be same as minus 3, right? Because these two entries are same. That's the only way, right? So that means k equals to minus 3 plus 1 minus 2 minus 1. For k equals to minus 1, for k equals to minus 1, we get the rank, the row columns are linearly dependent. Okay, I hope you understand it. Or you can also do one more thing. You can multiply the second row by 2k minus 1 and then subtract these two rows. Then you get something here which is the same. In fact, minus 3 minus 2k minus 1. Is there any doubt in this question? If there is any doubt, you can just raise a hand or type it in the chat box. If not, I'll proceed. Okay, let's go for question number 10. Let A be a matrix with rank of A same as rank of augmented matrix A augmented B, which is strictly less than n. Then linear system Ax equals to B has. This is, see, now rank of A is same as rank of A augmented B. That means the system is consistent. This implies that system is consistent. Since there exists a solution, that means this no solution is not an option. We just have to see how many solutions? So I have explained earlier, if the rank is strictly less than n, then there exists null space. Null space is non-trivial, so there exists non-zero, what do you say, vector such that AW is 0. Hence, you can create infinitely many solutions from one solution. Yes, the answer to this question is infinitely many solutions. I've already explained this, how to create infinitely many solutions from one solution before, for I think question number 2, 3, or 4. You can just go back and check. Okay, so then that's it for today. Questions are finished. If you have any doubts or any you have any topics that you don't understand and you want me to repeat or explain it again, you can what you can do is you can email me. I'll write my email ID here in the chat box. Then I'll try to explain it in the next session. Okay. Give an example of calculation of basis. Okay. Good question. Okay, so you want to, what do you mean by calculation of basis? How to find the basis of our space Rn, or to check whether something is a basis. So a given set of vectors. See, finding a basis, you will always have a basis as standard unit vectors 1, 0, 0, 0, 1, 0, 0, and 0, 0, 1, like this. That's always a basis. Basically, basis is a set of n, a set of n vectors which are linearly independent. That's all. So any set which has either less or more than n number of vectors is not a basis, first thing. And if the set has n number of vectors, then what you do is you check whether the set is linearly dependent or independent. Right? That's the procedure. For example, now consider R3. If I give you a set with the vectors 1, 0, 0 and 1, 1, 0. So question is this a basis? What's the answer? Okay. I mean, find a basis for a given subspace. That depends. The subspace. I mean, the natural procedure is you just start with one vector and find some other vector and see if those are linearly independent. Then you keep adding more and more vectors until the dimension of the vector space, and that's your basis. Okay, I got your point now. I have to give an example of a subspace now. Okay, let's consider R3 and the vector subspace U as the whole x, y, z such that 2x plus 3y plus z is, or let me make it complicated. Just x plus y plus z is 0. Okay, this is a vector subspace, and the question is give a basis of U. So let's pick some random vector from the vector space. 1, 0, minus 1 belongs to U, right? Okay, let's add another vector. 0, 1, minus 1 belongs to U. Now let's see if these two vectors, so let's say if these two vectors are linearly independent. You write those in column. What is the rank? You can directly see the rank is 2, but still one more calculation. Yeah, I mean two calculations here. First R3 plus R1, and then after that R3 plus R2. So rank is 2, hence the set is linearly independent. Now you add one more vector, maybe 0 or 1 minus 1 0 also belongs to you, and then you see if these three vectors are linearly independent. Oh, they are not linearly independent. Oh, yeah, of course it cannot be, because the dimension of this vector space is 2. Okay, but this is okay. This is a very, what do you say, crude force method to just randomly pick the vectors until the dimensions and then see if that's a basis. Other way to do is, now you see how elements in the vector space look, right? X plus y plus z equals to 0. That means you can write the third vector as the negative of the sum of first two, right? That means any vector x, y, z can be written as x times the vector 1 0 0 plus y times the vector 0 1 0 plus z times, oh no, wait, not like this. I can write x, y, and z I'll write as minus x minus y. That means this is x times 1 0 minus 1 plus y times 0 1 minus 1. That's all. For any vector x, y, z, you can represent it in this way: x times this, y times this. That means these are spanning set. Okay, this won't immediately become basis. This is a spanning set. So you just have to see the linearly independent vectors from those, and that will be your basis. Okay. In this case, all these two vectors are linearly independent. Hence, this will form the basis for the vector space U subspace. I hope this is clear. There are two methods I have explained. The most recent one, this one is more good, better than the previous one. Is it clear? Okay. So any more doubts you have? If there are no doubts, we can wind up for today. We'll meet on the coming Tuesday at same time, 6 to 8. If there is no doubt, we can leave the session. Session's over. What's it? Assignment to model questions. No, not, I mean, no, not today, I guess. We will start full assignment to, I mean, in the next session, Tuesday. Today my health is not so good, so I don't think I can do for the 2 hours. Sorry for that. Okay, first floor. This first question. Then says number 2. You want screenshot? You can take. I will share this whole PDF, by the way. You don't have to take the screenshot. I will share the whole PDF. Don't worry. Along with also this video recording. What do you mean by assignment to model question, by the way? The assignment 2 in the current semester course, you are saying? Course that's going on. I don't have those assignments right now. Maybe I'll write it down. The assignment 2 question number. You can tell me what question number you want the explanation for. So I'll give. Assignment 2 question number. Do you have the question number, or you want the explanation for all the assignment, the whole assignment? Let's see, if time permits, I will explain as many as possible. Okay, assignment 2. Okay, so if there are no doubts, see you all in the next session. I will close the meeting now.